Hi everybody. So this is our last lesson for this unit. And we're going to go back and we're going to look once again at limits. So remember, if when we had a limit, okay, we often had a function, f of x. And with a limit, the function was usually approaching a certain value, okay? So for example, it could be the limit as x approaches 2 of x squared plus 3x, okay? And with that limit, you usually substituted in that value of 2. So in this case, as it approaches 2, it'd be 2 squared plus 3 times 2, okay, which is 10, okay? That's usually how we see limits written. What we're going to look at today are limits where we have one function divided by the other. Okay, so you have the limit as x approaches a certain number. Okay, could be anything, could be 0, could be infinity, which is infinitely large, or it could be a number. It could be 1, 2. If we're talking about trigonometric functions, it could be something like pi by 2 or pi. Okay, or like I said, it could be 0 or infinity, or it could be something like 1, 4, 7, etc. Okay, any of those kind of things apply. And when we have a function that's 1 divided by another, an example of this might be that we have sine of x divided by x. Okay, so what we do in this situation is I'm going to talk about something called L'Hopital's rule. Okay, one of my favorite calculus professors in university called it the hospital rule. Okay, it's spelled the same. It's named after a mathematician who developed this somewhere in the 17th century. Okay, so what we're going to look at here is when we have two functions divided by each other, u of x divided by v of x. Okay, we look at the situation where as each function approaches that number a, it either comes up with one or of two scenarios. Okay, either it's 0 divided by 0. So in other words, both of these functions, u of x and v of x, approach 0, or they both approach infinity, okay, being a number so large that it's indeterminate. So both these are called indeterminate forms. And when this comes up, oftentimes you can calculate the limit, but you have to use what's called L'Hopital's rule. And what that is if you have a situation like this, okay, where it equals 0 over 0, or infinity divided by infinity, and the bottom function, okay, so the function in the denominator, v of x, cannot have a derivative of 0, okay? So v of x has to be something like, let's say it's 2x plus 2, okay? So if you took the derivative of it, that would just be 2. Okay, so the derivative of the function in the denominator can't be 0. Then you can find the limit by separating these two functions, whatever is in the numerator and whatever is in the denominator, and finding the derivative of them, okay? And then doing the exact same thing, finding the limit as that function, as x in that function approaches a, okay, or whatever it may be. Okay, so what I want to do is use this rule. It's one of my favorite rules in calculus, and I want to show you 4 examples where this would be used. Okay, so let's look at our first example. Evaluate the limit as x approaches 4 of 2x minus 8 divided by x squared minus 16. So the first thing you do when you solve these questions is you try and solve the limit, okay? So if we do that, we have the limit as x approaches 4 of 2x minus 8 divided by x squared minus 16. And if we substitute 4 in, again, because we're trying to figure out what this equals when x is 4, we have 2 times 4 minus 8 divided by 4 squared minus 16. which gives us 8 minus 8 divided by 16 minus 16, which is 0 divided by 0. So because it's 0 divided by 0, we can use L'Hopital's rule. Okay, so when we do that, okay, we look back at the function. All right, I'm going to write using L'Hopital's rule. We set everything in the numerator as the function u of x and everything in the denominator as v of x. Okay, so I'm going to rewrite the limit as x approaches 4 of u of x divided by v of x. Okay, and what I'm going to do is I'm going to let u of x equal 2x minus 8 and v of x equal x squared minus 16. Okay, so with L'Hopital's rule, remember we treat these separately, so we can do the limit, right? This is the same as taking the limit as x approaches 4 of the derivative of each of these functions individually. So u prime of x divided by v prime of x. Okay, so if we do that, our first step is we have to find the derivatives. So we look at the derivative u prime of x, and that's simply equal to 2. Okay, so we look at taking the derivative of 2x minus 8. And v prime of x, the derivative is simply 2x, right? Because we have x squared minus 16, so it's just 2x. So now, to use L'Hopital's rule, we just substitute those derivatives in. So we're left with the limit as x approaches 4 of 2 divided by 2x. Okay, so now if I substitute 4 in, we get 2 divided by 2 times 4, which is 2 divided by 8, or 1 divided by 4 in lowest terms. Okay, so I'm showing you how to use this rule. I'm not deriving this rule because it is very advanced calculus to show you why L'Hopital's rule works. But it's one of my favorite rules because it's just something, when you break it down, you're simply taking two derivatives, okay? The derivative of the numerator and the derivative of the denominator, and solving. So it's something that's so simple because taking these derivatives are just fundamentals that we've already learned, and it allows you to solve what is seemingly a complex limit. Okay, so this was example 1. Let's look at a few more examples. So this example is a little different, has a trig function in it. So evaluate the limit as x approaches pi of 2 sine 5x divided by x squared minus pi squared. So what you need to remember about this is when you have sine and cosine and tangent functions, you have to remember, we talked about at the very start of this unit what their graphs look like. So sine and cosine are recurring functions, they're cyclical. Okay, so if we look and we start at a point 0, the sine function is a simple wave, okay, that keeps repeating, okay, and it has a maximum and a minimum. And in the base case, the maximum, okay, is 1, and the minimum is -1. So this is the sine function. That's just sine of x. And each of these periods in the base function happens every 90 degrees. Okay, and remembering back to radians, if I can rate this as 90 degrees or pi by 2, which means at the next piece, that's 180 degrees, that's going to be pi. Okay, so at that point it equals 0. Then at the next function, it'll be 3 pi by 2, or 270 degrees. And at the end of the cycle, it's 360 degrees, or 2 pi. Because remember, when it comes to circles, there's 2 pi radians in one circle. Okay? So I'm not expecting you to know all of the intricacies. Okay? When I look at these questions, it's going to be one that's, a pi by 2 or a pi. okay? Because those are easy to identify. So in this case, if we go back to our limit and we substitute in pi, remember that's our first step, we have the limit as x approaches pi of 2 times the sine of 5x divided by x squared minus pi squared. So if I substitute in pi, I get 2 times the sine of 5 pi divided by pi squared, because I'm substituting in, minus pi squared. So remember, sine and cosine functions are cyclical, meaning that this wave is going to continue to happen, okay, again and again and again. So at pi, 2 pi, 3 pi, 4 pi, 5 pi, because it's cyclical, it's going to be 0 at every one of those. So at sine of just pi, it's 0. But remember, because it's cyclical and repeats, that means the sine of 5 pi would also be 0. Okay? So what that means is we have 2 times 0 divided by pi squared minus pi squared is 0. So we're left with 0 divided by 0. So again, what that means is it's an indeterminate. We have either 0 divided by 0 or infinity divided by infinity. So we can try using L'Hopital's rule. Okay? So if we do that, okay, remember for L'Hopital's rule, it's the limit as x approaches pi of what we have right now, u of x divided by v of x, is the same as the limit of x approaches pi of u prime of x divided by v prime of x. Or in other words, the derivative of the numerator divided by the derivative of the denominator. So we have to set u of x equal to the numerator, which is 2 sine of 5x, and v of x equal to the denominator, okay, which is x squared minus pi squared. So if we find the derivative of each of these, starting with u of x, u prime of x is equal to 2 cosine of 5x. And remember, because what's inside the brackets here is not just x, we have to take the derivative. So the derivative of 5x is simply 5. So u prime of x, simplifying, is equal to 10 cosine of 5x. V prime of x, okay, remember, we're starting with x squared minus pi squared, is simply 2x. Okay, because pi is a number, so the derivative of a number or a constant is just 0. Okay, so we can now substitute these values in. So if we do that, we get the limit as x approaches pi of u prime of x, okay, which is 10 cosine of 5x, divided by 2x. Okay, so we talked about the sine function, okay? This would have been back several math classes ago. That's why I'm going over it with you again. Remembering these values and what they approach will just take practice, okay? So I do recommend that you look at our review exercises after this lesson, okay? So if we have cosine, remember back from our first lesson, cosine is actually out of phase by pi by 2 or 90 degrees from sine. So it starts at the maximum, which is 1, goes down to 0, to -1, back up to 0, okay, and back to 1, okay? And again, these follow the same, 0, 90 degrees, or pi by 2, okay, is at 0. At 180 degrees, or pi, okay, it's at its lowest point, which is -1. At 3 pi by 2, or 270 degrees, it's back at 0. And then at 2 pi, or 360 degrees, it's back at 1. And remember, this cycle continues, okay? So it's cyclical, keeps going. That's the base function cosine of x. And remember, because it's cyclical, if you have cosine of 5x, that's simply the same. Okay, so the cosine of pi, or 2 pi, 3 pi, 4 pi, 5 pi, they're going to be the same number. All right? So if I now substitute pi, knowing what the graph for cosine looks like, I get 10 cosine of 5 pi divided by 2 pi. So remember, the cosine of 5 pi should be the same as the cosine of pi, right? Because it repeats. So if we go to pi, the value is -1, okay? So if I substitute that in, I get 10 times -1 divided by 2 pi. And if I simplify that, I have 10 times -1 is -10 divided by 2 pi. Or you can write this as -5 divided by pi. Okay? So again, I showed you the basic sine and cosine graphs. Okay? I'm always going to give you a question that has something like a pi by 2 or a pi, okay? One of these base kind of values to start with, okay? I'm not going to say, pi by 4, okay, which is in between, which is actually 45 degrees. I won't ask you those, all right? So brush up on these. Go back to our first lesson where I talk about them being out of phase between sine and cosine. That was when we talked about the derivative functions, okay? And just know that knowing the basics of those will make these questions go pretty quickly, okay? So let's look at a different question here, okay? So no more sine or cosine for right now. Let's look at the limit as x approaches infinity of 2x squared minus 3 divided by 2x plus 4x squared. So infinity is a number so large, okay, that if you have an instance where maybe you have infinity plus 1, it's still infinity. Infinity plus 1,000, it's still infinity because it's so large, okay, so it's indeterminately large. So we're going to start by substituting infinity in. So we'll get 2 times infinity squared minus 3 divided by 2 times infinity plus 4 times infinity squared. Okay, so infinity squared is simply infinity. It's too large, right? And even if you try and subtract a small number off, like 3, it doesn't matter. It's still indeterminately large. So we're left with infinity divided by infinity, okay? Because the number is just so large. And again, when you have that situation, it's indeterminate, so we can try and use L'Hopital's rule. So if we do, using L'Hopital's rule, we have the limit as x approaches infinity of u of x divided by v of x. And it's the same as doing the limit as x approaches infinity of the derivatives, u prime of x divided by v prime of x. Okay? So everything in the numerator, you let u of x be equal to. So u of x is equal to 2x squared minus 3. V of x is equal to 2x plus 4x squared. Okay, everything in the denominator to make this x look a little nicer. So if we take the derivatives, u prime of x is equal to just 4x, okay? Going back to the u of x equation. And v prime of x is equal to 2 plus 8x. Okay? So if I substitute these values in, all right, we get the limit as x approaches infinity of u prime, which is 4x, divided by 2 plus 8x. So if we substitute in infinity, we're left with 4 times infinity divided by 2 plus 8 times infinity, which again is infinity over infinity. So you might stop here and think, oh, I'm done, right? I did it as a derivative. Well, no, we're still at an indeterminate. We still have infinity over infinity. So the benefit of L'Hopital's rule is we can just do it again, okay? Because we're still in the same form, infinity divided by infinity. We didn't get anywhere. So you can keep doing it as long as you have an indeterminate that comes up, and as long as the derivative in your denominator is not 0. Okay, so in this case, both those apply. So that means we can write this again. So the limit of x approaches infinity, sorry, I'll write infinity a little bit nicer here, of u prime of x divided by v prime of x is equal to the limit as x approaches infinity of u double prime of x divided by v double prime of x, or the second derivatives. Okay, it doesn't make any difference. You can still do it again. So if we do the second derivative, so u double prime of x, for the first case, starting with 4x, the derivative is simply 4, and v double prime of x is equal to, okay, again, starting with 2 plus 8x, is simply 8. Okay? So if we substitute these values in, okay, we get the limit as x approaches infinity of 4 divided by 8, which is simply 1/2. Okay? So the trick in a lot of these examples when you have infinity is you have to keep doing the limit or taking the derivative until you typically don't have an x in there, right? Because anytime you have something multiplied by x, wait, in this case, infinity times a number, it's always going to be infinity. But in this case, we were just left with numbers, okay, 4 and 8. So we were able to substitute that in and find the limit. So as x approaches infinity, this function, 2x squared minus 3 divided by 2x plus 4x squared, will simply go towards 1/2. Okay? A lot of times how you'll see those graphs is when x is approaching infinity, okay, you'll have something like this, okay? Or maybe you'll have something like this, okay? But in other words, as x approaches infinity, the value here approaches 1/2. It never actually reaches 1/2, right? Because that curve goes on forever. But that's the number that it's approaching, okay? Okay, so let's look at one last example. You'll kind of see that with each of the 4 examples, I'm trying to introduce something that's a little bit different. Okay, so we saw a function with sine. We saw a function with one that had a double derivative. Okay, so the L'Hopital's rule twice. We saw kind of our basic starting point one. And now this one I'm introducing a different function that we've learned the derivative of. Okay, so ln. So evaluate the limit as x approaches 1 of x squared plus 2x minus 3 divided by ln x. Okay? So in this case, we're going to start by evaluating the limit. So we have the limit of x as x approaches 1. So if we substitute in 1, we get 1 squared plus 2 times 1 minus 3 divided by the ln of 1. Okay, so what we'll look at here is in the numerator, we have 1 plus 2 is 3, minus 3 is 0. And for ln, remember, for a logarithm or ln, okay, so for ln, it's the same as log with the base e. So if it's log of base e to the 1, okay, that's the same as writing ln 1. What that means is e to some value x has to be equal to 1. So remember, for any of these functions, to equal 1, the exponent would have to be 0. So that means the ln of 1 is 0, right? Because remember, what this is solving for is it's solving for this exponent, okay? So we end up with 0 divided by 0. Okay, so again, it's an indeterminate form, and we can use L'Hopital's rule. So in L'Hopital's rule, we have the limit as x approaches 1 of u of x divided by v of x. And that has to be equal to the limit as x approaches 1 of u prime of x divided by v prime of x. Okay, so everything in the numerator is u of x. So let u of x be x squared plus 2x minus 3. And v of x is the denominator, in this case, ln of x. So if we take the derivatives, u prime of x, that's equal to 2x plus 2. And the derivative, okay, of ln, remember, is 1 divided by, okay, whatever is in the brackets, in this case, x, times the derivative of what's in the brackets. Okay, so the derivative of x is simply 1. So we're left with just 1 divided by x. So if I substitute these values in, we get the limit as x approaches 1 of 2x plus 2 divided by 1 divided by x. So if we substitute in 1, we get 2 times 1 plus 2 divided by 1 divided by 1. So 1 divided by 1 is simply 1. And the numerator, 2 plus 2 is 4. So we're left with 4 divided by 1, or just 4. Okay? So this is one that's using ln. So I just wanted to give you an example of that as well. Okay? Remember, we talked about what a log and ln function were in a previous lesson. Okay? So again, you might have to go back, maybe do some review of those if that wasn't immediately apparent to you, or after some thinking back to that lesson, if that wasn't apparent to you, just brush up and maybe do a few of those examples. It should come back to you. Okay. So this was a short lesson. It's the last lesson of the unit before your test. So I've given you a list of practice problems here. I do recommend that you stick to doing these practice problems only. Okay, so I've selected them just because some of the other ones get into some concepts that maybe we either didn't talk about in this lesson, or items that we didn't kind of brush up on. So I do recommend you look at just these only. Okay, if you have any questions, please send me an email, bring them to our tutorials, and I'd be happy to help. Thanks, everybody.